All right. Now let me just give me a moment here as I switch spots. I think we have not lost anything. Don't you love technology? Okay, here's the cool thing though. I don't know if it's cool or completely pathetic, but that I have three computers located like 3 feet apart from each other. So that was a quick fix, wasn't it? So the other day when I was doing the exam, I was doing it from this computer. Now, I'm going to tell you right now, the biggest problem, can you see the light in the background? Did you see what just happened? Did it go light, dark?
Oh, yep.
This one here, for whatever reason, when I wear dark, it does this light dark thing. So I may have to stand away from the screen, you know. So anyway, I think we are recording right now. Let me get my map. Okay, good. We are recording. So I'm going to now, there we go. Whoop. That's you. I don't want, why is it doing this? Try one more time. There we go. Now, we'll make this work. I don't know exactly what's going to happen, but the other lecture is still, it's converting, so we didn't lose it. It's not licensed cyberspace. My only concern is going to be the quality. Okay, I just don't know that it was kind of sketchy as far as I'm concerned for most of it. So let's go ahead and continue. What we're going to do now, this concept of asymptotic convergence is basically the idea that not an asymptote, but that curves basically kind of like turn into other curves. Okay, let me go ahead and get rid of that thumbnail. So I want to consider the following graph. There we go. I want to consider the following graph. Y equals x to the fourth minus x squared plus 1 over x squared minus 1. That's kind of a crazy wild graph, okay? So if I said, let's graph this on a graphing calculator, we've got all sorts of goofy stuff going on here. So I'm going to do that on my graphing calculator. All right, so my window, yeah, this is where I'm standing. My window, let's see, let's go from maybe -5 to 5.
There's 2 asymptotes here.
You're right.
And it's looking like
Y minimum -10. Hold on, Y max. Okay. As I can wait for that. There we go. So, can you all see what's going on here? Now, by the way, do you see asymptotes on a graph, or can you all tell there's going to be 2 vertical asymptotes there? Can everyone tell that by looking at the graph?
Yep.
Yes.
Okay, so what I've got, the recycle guy finally decided to show up. You can hear him banging around outside. So when I graph this thing at x equal ±1, I got this, and then it looks like my graph's kind of going, let's see. When x is 0, y is going to be -1, so it's going to go like this. And then over here, it's doing something crazy and maybe something crazy. Okay, this is completely out of control behavior. That's cool. All right. So what I'm going to do is I'm going to take the exact same graph and I'm going to change my window. I'm going to step back. Okay. And what I mean by step back, you know, I don't want to be standing up close to the graph. I want to go to the other side of the room, maybe even the other side of the street, and say, will it look different to me? Right now, my window is -5 to 5 in the x, -10 to 10 in the y. I'm going to make it just for fun, -100 to 100. Okay, that's not, I mean, -5 to 5, -100. That's, you know, I'm zooming out 20 times. That's not out of control, I hope. Okay, now, because of the disparity in the exponents, I'm going to have to make the y max much, much bigger. So let me make the y max, how about 10,000? Okay, I won't touch the y min at all.
Well, it looks like a parabola.
Now, something really interesting is taking place. By the way, I didn't change the graph. I only zoomed out on my window. Yeah, it looks like, it doesn't just look like a parabola. It looks like exactly y equal 1 over x squared. Okay, what just happened? All I did was I said, let's just make our window a little bigger so we can widen it up. And then as a result, I see a totally different graph. Okay, this is the whole point. Why do I see a parabola? Why don't I see all this stuff anymore? Because if I do the longer synthetic division on this one, this is equal to x squared plus 1 over x squared minus 1. You can do a quick check. If you put this over a common denominator, you get that. And as x gets bigger and bigger and bigger, hold on a second. I'm teaching. As x gets bigger and bigger and bigger, what do we call this term again? What do we call that term? Anybody? Starts with a T.
Transient.
Transient term.
Oh,
You can't take a limit and have that go away. No, no, no. A limit affects all the x's. But what's happening is its contribution is getting less and less and less. Another way to think about it is, if I said, what's the difference between this graph and y equals x squared? That's the difference. Oh, so here's the correct way of saying this. You're gonna like this. This is what the symbol means. Most people use it incorrectly. This is asymptotic to x squared. The graph of y equals x squared and this graph here are asymptotic because it means as x gets bigger and bigger and bigger, you just saw it for yourself on the screen. You couldn't tell the difference between y equals x squared and my crazy graph because the difference between them, which was the 1 over x squared minus 1 term, that difference is approaching 0. So we'd say that this graph is asymptotic to this one. Asymptotic means, again, they kind of turn into each other. It doesn't have to be a line. When it's asymptotic to a line, the line is called an asymptote. This isn't involving asymptotes. This is just a picture where I can't tell the difference. And here's why this is kind of cool. If I said, without a calculator, can you give me a rough estimation of, evaluate this at 1,000? Well, 1,000 squared is 1,000,000. So I'd say, I'm going to estimate the y value here at 1,000 to be a million. Now, if I do it on my calculator, I'm going to find it's almost exactly 1,000,000. It's a tiny bit off. But the nice thing about asymptotic convergence is I can use the simpler one to do estimations of the complicated one. All of statistics is based on this concept. If you've ever had statistics, that's what everything is based on. That's why you can use samples that are finite to make conclusions about populations, which technically are almost infinite, because you get the convergence. The larger the sample, the more it converges to the actual population. And a lot of times you can do really simple calculations of complicated things because you know they're going to be close. They're not equal, but they're so close it didn't matter. And that's kind of a cool thing. This is kind of where we're going to be going really soon, is this concept that I can use a different function, okay, to do this. So with that said, the next test, okay, is one of the most powerful ones, and probably the most powerful one we're going to learn today. This one is called the limit comparison test. Okay, now here's the idea. I'm trying to figure out if a particular series converges or diverges. I would like to compare it to something where I already know the behavior, but that's only meaningful if I believe they're going to behave essentially the same way. And that's really the key. I have to believe they're going to have the same kind of behavior that, one thinks it's the other one, in other words. So if I said, I want to determine the behavior of something like, let's use one we already did. We did this using the integral test. We can actually do a direct comparison with 1 over n squared, okay? But I would like to do a limit comparison. But what would I compare it to? Well, clearly I would compare it to 1 over n squared. Because as n gets bigger and bigger and bigger, this thing's going to look more and more like 1 over n squared. So we'd say it like this. Compare to the sum, and always the sum. You can't compare a sum to an individual term. You're comparing a sum to another sum, a convergent p-series. Now, the reason it's so important that I actually say this is because the conclusion that I get at the end of the problem is either going to be that this guy converges or diverges. but it has to match what I compared it to. Oh, so if I say the wrong word here, I'm going to get the wrong conclusion. If I don't say anything here, then I don't actually have a conclusion. Now, the way the limit comparison test works is you're going to take the ratio of the two, basically the two functions, if you want to call them that. So the idea is sort of generically. I'm going to give you a really simple generic. Let's say we want to use this series to show the behavior of, let's say, this series. I know the behavior of this guy. I don't know the behavior of this guy, but I think they're acting the same. That's what I'm starting with. I believe they have the same behavior. So then what we're going to do is take the limit as n goes to infinity of an over bn, or the limit as n goes to infinity of bn over an. It does not matter which way you do it. If your result is a finite value that's not zero, you know, your result is 5, your result is negative 2/3, your result is a finite value, then basically you're saying one of these is acting like a constant multiple of the other. And what's the constant multiple? Well, whatever your limit is. So what you want to get is finite, not zero. If you get a limit of 0 or infinity, it means the test failed. It means you compared it to the wrong sum. It means you compared it to a sum that doesn't act similarly. But if your limit is finite and non-zero, then it means you did a perfect test. So when we do this, okay, I'm gonna erase this part here. We're going to do the limit now, not of the sums, but of the individual terms. Now we can either do 1 over n squared over 1 over n squared, or we can do 1 over n squared over 1 over 1 plus n squared. We can do either one. But in both cases, clearly, I'm going to have to move the denominator, right? I'm going to have to manipulate that. Both conclusions should be the same. Both conclusions are going to be that I converge, or both conclusions I diverge. It never matters which one you do. I have a preference personally. I generally will do this one because I don't want to monkey with my original argument. I want to kind of leave it alone. If I flip it over and take a reciprocal, I could inadvertently lose something. I'm not just paying attention well enough. So I'm going to do this one. So this is equal to the limit as n goes to infinity of 1 over 1 plus n squared times n squared over 1. And that will equal the limit as n goes to infinity of n squared over 1 plus n squared. And what is that limit? I don't need to do any more work. What is that limit? Anybody?
Just 1.
It's 1. The degree of the numerator and denominator are the same. When doing this type of test, you should always be getting that the degree of the numerator and denominator are the same. That limit is 1. Is 1 a good answer? Yeah. That means that basically these have identical behavior. I mean, literally, they're acting like one times the other. And because that one converged, I can now conclude that this one converges. So we'll say it in so many words. Therefore, the sum converges by the limit comparison test. That's still too long. Anybody got a good idea?
LCT.
LCT. These are the only ones we abbreviate. Direct comparison test, limit comparison test. Everybody
is 3 dots common for therefore? Like, is that appropriate?
Yep. Yeah, that's a universal symbol. That's by the way, that's not a math symbol. That's an English symbol. But we use it in math all the time because 2 reasons. One, therefore just takes so long. And believe it or not, it's even better. Do you know that most math people, when they write therefore, misspell it? By the way, I'm one of those people. There's actually an E at the end. Almost 100% of the time when a math person writes out the word therefore, they forget the E at the end and just looks silly. No, therefore.
Professor, another question. So
when we're doing the limit comparison test, are we always comparing it to something that we already know the behavior of?
Yes, yes, that's critical because otherwise now you got two wild cards. We're going to do a couple more of these. And it's usually a P series, by the way. That's the most.
Okay. And so if it's convergent and we compare it and we get an integer, then we know that it our original also converges. But can we also compare it to diverging?
We're going to do both. Exactly. It's,
okay.
By the way, I'm going to write down a series. The series either converges or it diverges. We can't control that. Okay. Our job is just to discover it correctly. So if I have a series that diverges, there's no possible way of coming up with a conclusion of convergence correctly. My goal is to correctly determine what it's doing with the least amount of effort. So in other words, the most appropriate test at the time. Let's consider another one. I'm going to make it a little more complicated because we love complicated. All right, I've got 3n squared minus 4n over 6n cubed plus 5n squared plus 1. Oh my goodness. By the way, I really don't want to do an integral test on this one. That would be nightmarish. You might be able to, but it might take you a while. Nope, integral test is out. Can I try a direct comparison? No, it won't work either. Oh my God. Well, what can I compare this to? What P series does this one act like? Actually, this is the easiest thing we're going to do the rest of the way. What P series does this act like? I have a second degree polynomial over a third degree polynomial. There's only one P series that looks like that. Which one is it?
1 over n.
1 over n. And how did you know that? You're right.
Just if you take the leading terms and you divide them.
The difference. The degrees are 1 apart, so I want an exponent of 1. It's that simple. And it's almost too simple that we could have missed that. I have a degree difference of 1. So if I said multiply top and bottom by 1 over n squared, oh, then I'd have a constant and an n on the bottom. You don't need to do that. So we're going to compare to the sum of 1 over n. Again, I'm comparing to a series, a divergent harmonic. And again, if you said P series, you'd be correct also. Now, Tom asked the question, would we ever compare to a divergent series? We are here, and the reason is we believe that this thing is going to diverge because we believe it has behavior similar to this. We will confirm that with our actual test. So the test looks like this. I now want to take the limit of either this divided by this or this divided by this. I'm going to show you the simplest, fastest setup humanly possible. You're going to like this because this is what I would prefer you to do. Now, I want to divide by 1 over n. In the process of dividing by 1 over n, isn't that going to be exactly the same as times what?
N.
Does everyone understand? I just divided by 1 over n. So this keeps me from having to rewrite the problem 2 or 3 times before I start working. I'm dividing by 1 over n, which is equivalent to multiplying by n over 1. That's why I typically will leave this one alone and manipulate that one, because then it makes this writing just a little bit easier. Now, let's work that n in there because it doesn't quite look like something I can work with until I multiply that in. I now have the limit of a third degree polynomial over another third degree polynomial, and that limit is what?
1/3.
Close.
It's
3/6, which is 1/2.
6 or
1/2. Okay.
1/2.
1/2. Is 1/2 a good number? 1/2 a great number. It's a perfect number. Why? Because it's finite and it is not 0. In simple English, what does the 1/2 mean? It means that this series acts like it's about half as big as this series. That's it. This series term by term is about half as big as that one. Not exactly. The limit was 1/2. Oh, okay. But that one's infinite. Therefore, this one is also infinite.
Understood.
Therefore, Yeah, everybody likes this one because it's just not difficult mathematically. And the best part is you really don't have to think too hard when you're saying, what should I compare it to? Therefore, this diverges. Now, why diverges? Because that was the behavior of the thing I compared it to, and I have a very successful comparison by a limit comparison test. Okay, kind of cool, huh? It's like, that wasn't that bad. That really wasn't bad at all. It turns out there are series where you could actually use an integral test on the series, but also use a direct comparison test on the series. And you could also use maybe even a limit comparison test. There are a few out there that you could use multiple tests on. Well, if I had an integration problem and I said I need the antiderivative, and you go, you know, I can use this technique, I can use this technique. Which one do you use? The answer is yes. Whichever one you see. If everything that you did was valid, then it didn't matter which one you chose. There are problems out there where multiple tests will actually work and give you the right conclusion. Given the choice, you don't generally want to run to the integral test because it means you're starting the problem with an improper integral that automatically is a little more complicated. If I can do a direct comparison, I will, but more often than not, these types of tests may not work. So the limit comparison is most people's fallback because I already know it's going to work just fine. Now, I'm going to give you one that's way more challenging. All right, I would like the limit as n goes to infinity of, let's say, n to the 7/2 minus 3n to the 3/2 over 4n to the 6th minus 5n squared. Boy, vey. That's not even a rational function on top. Any ideas on this one?
Can we figure out what the leading term would be and then compare that with the p series, knowing the p value is going to be greater than?
Give
Is
me
that-
a very specific exponent you want to use.
Is that
It would
3/2
be-
or some?
That's 7/2 and 3/2, yeah.
Okay, 7/2.
So that would be this
Or is it supposed to be limit or sum?
Oh, I'm
5.
thank you for that. Yeah, I'm getting
Right.
ahead of myself. Thank you. That's a sum. Yeah. Does it matter? Yeah. Yeah. It matters greatly.
So it would be 1 over n to the 5/12 or 5/2.
Which is one of them was correct.
5/2.
5/2. Do you all agree that the degree difference is 5/2? 6, 12/2, and 7/2 differ by 5/2. This is what I want to compare it to. Does that mean that this quotient equals this quotient? No.
No.
But we believe they'll have the same behavior because of that degree, that exponent difference. The rest of the problem should now quite literally self-navigate. This should actually take just a couple of steps because I made the right choice. If I make the wrong choice, it doesn't work. You can't force it. But we just made the right choice and we had to think about it. So I like what you guys said. Look at the highest exponent. What is the difference? That will always determine the p series you're going to choose. That's why I said earlier, choosing the correct one is actually pretty simple most of the time. This one required a little more thinking because I threw a fractional exponent at you. But it turns out the algebra is not going to be any harder. So we want to do the limit as n goes to infinity of this over this, which would be the same as times this. You don't have to write over 1, but just mentally, okay? Now, if I multiply that out on top, now rules of exponents, right? When you multiply things with the same base, what do you do with the exponents?
You, Adam?
Add them. 7/2 plus 5/2.
Someone said my name.
12/2. So that's x into the 6th. And that would be into the
8/2, 4.
4. Now, is this intimidating? That looks pretty easy, doesn't it? Oh, well, what's this limit?
1/4.
What if I have the wrong exponent? By the way, it's no matter how good you are, nobody gets through everything unscathed. You're going to make a mistake on occasion. Let's just suppose I had the wrong exponent here. That means at this point in the problem, one of two things. I would either get a 0 or I would get an infinity. I'm guaranteeing you're going to get one or the other, depending on if I choose any exponent other than 5/2, I will get a 0 or an infinity. A 0 or an infinity means I made the wrong choice. They're not comparable. Okay, that's it. So I got a finite non-zero number. See, the reason I say it like that, because 0 is finite, but 0 means I made a poor choice. There was a difference. They didn't behave the same. Because that's finite non-zero, that means that I can say that these have the same behavior, and this one acts like it's about 1/4 as big as this. So if I knew whatever that added up to, this would be roughly 1/4.
Did you forget to write that it's a convergent P series?
Did we? Oh, you know what? We did. We did. Oh, good. Good catch. Nope.
Adam.
Working too fast. That's
How many
100
miles?
175 miles. Not sure if that 200 is pretty good. That, all right. He's just waiting for me to forget something so he can load those miles up. I know how that works.
I'm keeping track.
Convergent. Oh, believe it or not, I've had many classes where people gave me a list at the end of the semester. They'd actually kept track of every mile, and yeah. All right, a convergent P series. That's all I got to say. Why is it important? Because again, it's not the 1/4. 1/4 is meaningless. It's just a finite number. I can now say I'm going to have that behavior. So my original series, write it down correctly. Yaman understands this one because he does this a lot of times. You'll say at the end of the problem, and this converges by. I really like it when people state that.
Yeah.
This is the problem. And so my conclusion is this. I think this is good form. Anybody reading this is very obvious that you have the conclusion and you're making the conclusion about this, not about that. That was the tool you used to make the conclusion. Now, so far, would you say this stuff is not terribly taxing from an algebra standpoint? It's not bad at all. Now, I want to do one more example. This one sometimes throws people because I have actually used textbooks that give improper rules for this. They'll say things like, this has to be positive. Actually, it doesn't have to be positive. It never has to be positive. In fact, 50% of all the problems that exist, it's going to be negative. Yeah, so there are artificial rules out there that I don't understand where they come from, but it can cause bad conclusions. No, we do. All right, I don't want too many terms. It gets kind of busy after a while. So. There. I just need you to fill in a couple of things. I got almost everything there. I need you to fill in a couple of things for me. Well, doesn't that right there have everything to do with that right there? You agree?
Yeah. If it's one or more.
So I better get it right. What am I going to compare to?
1 over n cubed.
Y cubed. Isn't that a difference of 5?
No, that's not the leading term though.
Oh, now that one gets people sometimes. They're not looking. N cubed. That is definitely an n cubed. A convergent P series. Okay. I think I know what to do from this point on. I am now going to take the limit as n goes to infinity of 4n minus 6n cubed over 8n to the 6th plus 3n squared, divided by 1 over n cubed, so times n cubed over 1. We get really good at this really fast. So 4n to the 4th minus 6n to the 6th, 8n to the 6th plus 3n squared. And that limit is
Negative 6/8.
negative 6/8. Huh, we haven't had one of those. All right, I'll actually write negative 3/4, negative 6/8. Now, I've seen people do all sorts of wacky things. Oh, that's negative, therefore. Nope. There is no conclusion that can be made based on the sign of this answer, period. Any conclusion made based on the sign would be an incorrect conclusion because it'd just be a guess. That number is finite. It is not 0. So I did a perfect test. If that had been a 0 or an infinity, then I did a bad test. So therefore, my original sum converge or diverge?
Converge.
Converge.
Converges by the limit comparison test. Now, tell me something about it. It does converge. It's going to be a finite value. Tell me something about that finite value.
It's negative.
It's going to be negative. Whatever this converges to, this is going to be about negative 3/4 as big. Why? Starting with n equal 1, every single term of this series is negative. Do you agree? Every term in this series is negative, therefore its sum is negative. That doesn't affect convergence or divergence just because it's negative. That's an area that a lot of textbooks really struggle with because they'll avoid that problem and say, oh, you can't have negative terms. On Monday, we're going to look at series. The most general form of a series, believe it or not, is that the numbers actually alternate from positive to negative. That's the most common form of a series. So to say I can't have negative terms in a series doesn't make any sense when almost every series you ever deal with will be alternating signs. No, negative terms in a series is fine. And if it helps you, you're going, this troubles me. I don't like the negative. It's messing me up. Well, I'm going to show you something you can do. I'm not saying you should do. But if it helps you to justify what's going on,
Multiply by a -1.
not multiply.
Or like take out a -1.
Do you believe these are equal?
Yeah.
So if I did all of the analysis on this guy, I would have got a positive 3/4 and so on. And then I just simply slap a negative in front. There's no difference. This is why I have a problem with so many of the textbooks, and almost every one I've ever used. They avoid this problem like the plague, and they tell you, oh, in a series, every term has to be positive. Really? Because on Monday, every series you ever look at will have half its terms negative. Why would you throw an artificial restriction on there just to avoid one type of problem? No, this problem wasn't any harder than the other ones. And getting a negative number there, no big deal. It just meant one acted as a negative multiplier of the other. So that meant my sum was going to be negative. That's it. So the 3 tests we learned today are all similar in the types of problems you would apply them on. Now, the question a lot of folks have is, do I ever have to use the integral test? There is one situation, yeah, unfortunately you do. Sometimes you have to. So I'm going to give you a couple of situations here that come up. We don't see a lot of trig. We just won't see a lot of trig when we're doing series. You don't see sine or cosine. That's really, really unusual, okay? But you do sometimes see logarithms. Logarithms, when it comes to series, are not our friends. We don't like logs. We just don't. So there's 3 problems I want to look at. By the way, does anybody want to guess why I started all these at 2?
So that you don't have to deal with and being 1 and having
Log of 1
Uh,
is log of 1 is 0,
zero.
and so 0 over 1 is like
The first term of a series can't be 0. Ah, see, in other words, if I started at 1, then the first term of my series would be 1. Yeah, the first term of a series can't be 1. So, oh, that's why I'm starting at 2. I could have started later, but I'm starting at 2 because otherwise I'd say it's 0 plus. Now, these are 3 very different problems that have 3 very different ways I can do them. The first one is the following statement true? Is log n over n greater than 1 over n? Is that true or false?
True.
Is it always true? Well, log 1 wouldn't work. In fact, log 2 wouldn't work. Oh, but log 3 would. For all n greater than or equal to 3. That's why we throw that in sometimes. From 3 on, because log 2 is like 0.69. That's a little smaller. But log 3, that's bigger than 1. So you know what I'm going to do? I'm going to do a direct comparison because this is bigger than this. Okay, does everybody see that? Oh, I can do a direct comparison on this. This diverges because it's bigger than the harmonic series. Okay, now let me jump down to the last one. Sorry, that's a cube. True or false? If it helps you think of a graph, there's the log, there's the line. Is the log always smaller than n?
Yes.
Always. This is always true. And so what we'd say in this case, for all n greater than or equal to 2, because that's where I started. So that means then, oh, by the way, and that's 1 over n squared. So I would do a direct comparison with this and the sum of 1 over n squared to show this converges again by the direct comparison test. We don't love logs, but sometimes we get lucky. This is bigger than 1 over n. This is smaller than 1 over n squared. We got lucky.
Professor,
Yes.
is the first one when you did the comparison, is it n equals 1 or n equals 2?
Did I? Oh, thank you. Yeah, let's do. Should be the same. Thanks for catching that. So does everyone see that this is going to diverge by direct comparison because I'm bigger than a known? This one's going to converge by direct comparison because I'm smaller than a known convergent series. Evil. There is no comparison I can do here. All my inequalities would always be in the wrong direction. So the middle one, you have no choice. The middle one, you have to do the integral from 2 to infinity of log n over n squared. Now, or I should say log x. I'll do x. Now, we had a problem on the exam, I believe, that was really similar to this. This isn't a hard integration, but I don't love it. What technique must I use on this one? Anybody?
Integration by parts.
Integration by parts. My u would be the log, my dv would be the x, and then I'd actually be able to do it in one step. Oh, what's the big deal? Because then my antiderivative evaluated, I actually have to use L'Hopital's rule on my antiderivative because I'm going to get an indeterminate form. On my antiderivative, I'm going to have a log and an x as x goes to an, oh man. So integration by parts to do the integration and L'Hopital's rule within the solving of it. Neither one of those are killers, but the fact is those are 2 major calculus steps that I would have to perform in order to do this one. We didn't mind the first and the third. This is the only way. There is no other way to do this. Whenever there is a logarithm in an answer or in a problem, think of this. If there is a log in the problem, look and see if you can do a direct comparison. If you can, take it. If you can't, you have to use integral test. And that's pretty much the only time you have to do integral test. But I could have used integral test on this one. I could have used integral test on the third one, but the direct comparison was so simple. Okay, and it was right there in front of me because everything was just right. But you won't always get that lucky. So I wanted to throw this out at you because sometimes you have options I believe the quiz that I've asked you for this, I've got it somewhere. I believe the quiz I've asked you for this, you're going to probably do one of each of the tests, you know, or at least you have the opportunity to do one of each of the tests, just so you can get used to it. Tomorrow, the stuff we look at tomorrow, there is absolutely no overlap with any of the problems we did today, which is actually a good thing. So it tend to be less confusing. The stuff we did today, think of rational functions in general. I have quotients of polynomials. So everything we compared it to was usually some p-series, whether it was a direct comparison or a limit comparison. We were using p-series and the comparisons were pretty simple. Tomorrow, we're going to look at things involving exponential functions, you know, like, 2 to the n and factorials. They're completely different animals than what we did today. In fact, all of the tests we did today will not work tomorrow, and all the tests we're going to learn tomorrow, none of them would work today. There won't be any overlap of those guys. Okay, so that actually will make it easier in some cases to keep them separate. And we will round out, we'll learn techniques 4 and 5 tomorrow, and they're also very similar and close in nature, like the ones we did today are. All right, so I'm going to stop there. Whoops, I got multiple mouses on my table here.